In the previous video, we defined what are ADTs or abstract data types. In this video, we are going to cover the first ADT that we'll encounter in this course, which is the list ADT. So a list ADT basically describes an ordered collection of data where ordered means that there's some position that's available to an element. And this is basically a linear data structure because we have a linear ordering, which is you can go from one uh, position to another using some sort of a language construct. Also, all the elements have some position, as well as the list ADT provides us an opportunity to either grow or shrink in size, or they might have some fixed size depending on the implementation. There's no limit on the nature of elements, and what I mean by that is it can store any types of elements, not just integers. It could be a list of objects, it could be a list of strings, and so on. So let's see, using our framework that we had, which is ADTs comprise of two different things, which is data and operations. So what would be the data that is relevant for the list ADT? In this case, a list ADT should at a minimum have some items. Also, it should have the number of items a property, as well as the capacity, which is how much of the list is actually filled, or if it is growable or shrinkable to infinite lengths. There should be an implicit way to understand whether we can is if this data structure is bounded or this can grow infinitely. Some of the operations for the list ADT include read and write an element, add or remove an element, finding an element in the collection, counting how many elements are there in the collection, or traversing the list. Now, we are going to see some instantiations of this ADT in the form of two different data structures. The first one is array, which everybody should already know, and the second one is linked list, which you have already seen in programming too. So I'm going to go a little bit fast on these two data structures. We are going to comparatively see what do their performance looks like. So let's talk about arrays. So basically arrays are a data structure, a sequential or linear data structure that stores elements of same types. It has some indices where elements are stored. It also has a finite size because we are storing a certain number of elements. There are something called dynamic arrays, which include like array lists in Java, or in STL we have vectors, but we are going to skip them for now, which is like most languages. Let's say a common definition of array is they are bounded. And the next one is all of the elements in the array are of the same data type. Like they cannot store one object and another integer. So whenever we are defining an array, it has to have like same type of arrays, same type of elements. So we covered fixed size, we covered it stores similar elements. They are contiguous indices, which means like you have the indices from 0, 1, 2, 3 up till n, or n minus 1. Like we do not have indices which are jumping from one place to another, like something like 0 and then 15 and then 17 or so on. And finally, it allows random access, which is if we have an array, if we try to do something like array of x, we can go to that particular element using the formula that we have the array's head, or what is the location of the first element, and then we can multiply this. So we, let's say if we want to go to the third index, we can just do the location of the first index plus the location where we want to go to, which is the offset, multiplied by the size of each element, which is in this case, let's say if it is integer, it's 8 bytes. So if you do something like location plus offset into size, you can basically go to any particular index in constant amount of time, which we are going to see very soon. So what are the operations that are possible on this array or list ADT? In this case, we want to add certain elements as we previously saw, and we want to see how the performance works when we are trying to add elements in the beginning, in the middle, or in the end. Similarly, we want to see how it would work for beginning, end, and middle removal. So let's compare the performance, which is if you have an array that has some numbers. Now let's try to add an element in the beginning. So in this case, if we try to add, like, let's say 0 on the position 0, we need to shift all these numbers from this place to one step on the right, because we need to make space for 0. So in that case, shifting takes O of n complexity, because we are going to move n elements towards the right. Or we don't know, like in the worst case, there might be n elements, so we are shifting n elements. What about removing elements from from the beginning? So again, like if we try to remove this 1, we have to shift all the numbers which are on the right side one towards the left. So the removal will again be O of n. Next, if we try to add an element to the end, it's pretty straightforward, because we know the size is n minus 1, and let's say the array is filled till size n minus 2. So the new element would be added to n minus 1. And in that case, the addition of an element would be O of 1, because we know what is the size of this array, we know how much it's filled. Because let's say if we are trying to create our own array class, we can have two different variables. One is the size, which is how many elements it's storing, and the second one is capacity, which is what is the maximum size that's allowed. Like let's say if this array has size n minus 1, but it's only filling 3 elements, then the size of this array would be something like 3. Now, what about removing an element from the end? So again, we know that there's some size variable in our class or our implementation, so we can always remove the last element by using remove on the last element, and in that case, the complexity would again be O of 1. Finally, let's talk about adding in the middle. So adding in the middle will work again similarly to the beginning add, which is we we want to shift the elements on the right of the middle. So in that case, it would be again O of n, and removing would be similarly O of n. So let's talk about a little bit benefits of this approach as well as the drawbacks. So the benefits are constant time access. Again, I told you, like if we want to find what is present at array index 1 I, we can just do the location of the first element plus I into size of the type that is being stored in the array, because we know every location is storing the same amount of space, which is every location takes the same amount of space. So let's say it's 4 bytes. If we just do I into size of this location, we can go to any particular index in constant time, because this equation will allow us to go to any index in the array as it's contiguous in the memory. So that's one big benefit of it. And when we are going to talk about lists, we see that this benefit is actually removed, because you cannot just jump to any place in the memory in linked list, which is since the data is scattered throughout memory. Now, what about the drawback? The drawback is, let's say if you are trying to add some numbers in the front, which is if you are trying to add or remove numbers in the front, this takes linear amount of time, which can be very expensive in certain scenarios. So throughout this course, we'll be seeing different data structures, and you might be thinking which data structure is better than the other. We are going to see like none of the data structures are better than the other without a particular context, which is if you have a certain problem, the parameters of the problem will allow you to define which data structure to use, which is all data structures have some trade-offs when compared to another, and you have to use those trade-offs in certain scenarios. So In the next video, we are going to talk about the second way the list ADT is implemented using linked list. Thank you.